Project on coil guns. Today we're going to take you through our journey of building and testing a coil gun, exploring the fascinating world of electromagnetic projectile launchers. What is an electromagnetic coil gun, you may ask? A electromagnetic coil gun is a projectile launcher that uses a series of electromagnetic coils that, when given a current, creates a magnetic field, which then accelerates a projectile made of ferromagnetic material through a barrel, causing the material to isolate inside the solenoid. When the current is turned off during isolation, the material will continue to travel its path and create a projectile.
Our project began with disassembling a disposable camera and repurposing its circuit board to power our coil gun. We carefully wired a switch to control the current flow through the solenoid.
Next, we experimented with different solenoid configurations, creating 3 variations with varying number of coil turns. This allowed us to explore the effects of magnetic field strength on projectile acceleration.
In this test run, we used 2-meter sticks to measure the distance the projectile traveled. In the 600-turn solenoid, we used 1.5 voltage to create a magnetic field through the solenoid to shoot the projectile. We then used a sensor to measure the magnetic field strength produced by each solenoid. This data helped us understand how changes in coil turns and voltage influence the magnetic field and consequently the velocity of the projectile. In our 900 test turn solenoid test run, we did the same steps, and as we can see, our solenoid traveled a further distance compared to the 600 turn.
Do some theoretical calculations! That's me in the video.
Okay, so we want to start off by doing our theoretical calculations. And so right now we are going to do the 600 turn solenoid with a 1.5 volt battery. And so to start off, we need to calculate our resistivity. And so our resistivity equation is as written, where A is going to be the cross-sectional area. And I found this with the product description online. And the permeability of copper is going to be a constant. And our length is the length of wire that we used for our solenoid, which is going to be 546 meters. And so first we got to solve for R. We plug in our known values. By cross-sectional area, which is and if we plug all these values into a calculator, we're going to get 115.44 ohms. Okay, and so this is needed for our equation to find our current. And so this is the equation that we start off with. And so if we manipulate this, equals IR, we manipulate, because we're trying to find I, we have R and we have change in voltage. And so we want to do change in V divided by R equals our current, which we're trying to find. And in this equation, the change in V is going to be our voltage, which is 1.5, and we just found the resistivity of the solenoid. So 1.5 divided by 115.44 equals current. And we already did all these calculations beforehand. So our current goes to be and so now we want to find the magnetic field of the solenoid, which is something we measured in our experiment. And again, this is the theoretical values, which we did everything correctly. It should be pretty close to the values that we measured. And so we take it, this is going to be the magnetic field of a solenoid. And this mu naught is going to be a constant value. N is going to be the number of turns. L is the length of the solenoid, and our knowns right now is going to be N equals 600. The length of solenoid measured is going to be 0.0254 meters. And from over there, we now have our I value, going to be 0.01299 amps. And let's plug it in. mu naught, which is going to be, and we don't have to manipulate the equation in any way. It's going to be 4 pi times 10 negative 7 number of turns, which is going to be 600 in this case. I is going to be 0.01299 divided by the length of our solenoid, which in this case 0.0254. So our theoretical is going to be 3.856 5348. Which we are then going to compare to our experiment value. Okay.
The measured and experiential values in which these tables we can see the change in magnetic field and velocity values when using different voltages and turns.
Our results unveiled a clear relationship between the strength of the magnetic field and the velocity force onto the projectile. As we increased the number of coil turns and voltage, we observed corresponding increases in projectile velocity.
However, we encountered challenges along the way, such as insufficient voltage for certain solenoids and circuit board failures. Despite these obstacles, we persevered, troubleshooting our way to success and learning valuable lessons in the process.
In conclusion, our coil gun experiment provided a comprehensive exploration of electromagnetic principles from theory to application. By analyzing our results and addressing challenges head-on, we've gained invaluable insights into the intricacies of coil gun design and optimization.
Muchas gracias por estar con nosotros en este viaje. Nah, just kidding. Thank you for joining us on this journey through the world of coil guns. We hope our project has inspired you to delve deeper into the realm of electromagnetism and explore the endless possibilities it holds.
Remember, kids, science is all about experimentation and discovery. So don't be afraid to roll up your sleeves, tackle challenges, and push the boundaries of what's possible. Who knows what marvels you might uncover along the way?
I hear a magnetic field creating.
From all of us, thank you for watching.